Good evening, everyone. So we have been discussing the chapter called atomic structure, right? So we are done with the Bohr's model, we are done with quantum numbers, and we have discussed how to write the electronic configuration of an element, right? And also we have discussed a couple of principles like half-pass principle, Pauli's exclusion principle, Hund's rule, and all that, right? And we have discussed how to write the electronic configuration and how this Pauli's exclusion principle applies and all right, and all that, right, Kana? So today we'll be discussing electronic transitions, electromagnetic radiation, wave parameters, photoelectric effect, Heisenberg's uncertainty principle. Okay, fine. So, what are all the formulas we have studied in Bohr's model? What are all the formulas we have studied in Bohr's model? According to Bohr, in an atom, nucleus is present at the center of the atom and electrons are revolving around the nucleus, right? And these electrons are revolving in a particular path called orbit, and this electron got a particular amount of energy. If the electron is present in first shell, then it will have some particular amount of energy. If the electron is present in second shell, then that electron will have a particular amount of energy. There is a formula to calculate the energy of an electron. And what is the formula? What is the formula to calculate energy of an electron? And Bohr's model is applicable to what kind of atoms? We cannot apply this Bohr's model to all the atoms, right? Yes, Kana? So Bohr's model can be applied only to hydrogen or hydrogen-like systems. What is this hydrogen-like system? What is hydrogen-like system? An atom with single electron, right? So we can apply Bohr's model to hydrogen. We can apply Bohr's model to helium plus. We can apply Bohr's model to lithium 2 plus, because all these ions also got only one electron, right? So from Bohr's model, we can calculate energy of an electron, radius of the atom, angular momentum of the electron, velocity of the electron, right? Okay. Is my screen visible? What is half-pass principle? What is half-pass principle?
Electrons are arranged on the order of energy, ma'am.
Yes. So first we have to fill the electron which is present in lower energy and then to higher energy. Okay, fine. How to find whether the given orbital is of lower energy or higher energy? Is there any rule to do that? How to find whether the given orbital is of lower energy or higher energy? There is a rule called n plus L rule. If the value of n plus L is less, then that is considered to be the lower energy. Right? Fine. Okay, listen here. Let us say this is a hydrogen atom. Okay, and this is the nucleus. For convenience, I'm going to draw the energy levels as horizontal lines and not as concentric circles. So this is n is equal to 1. This is first shell. This is n is equal to 2. This is second shell. This is n is equal to 3. This is third shell. This is fourth shell. This is fifth shell, and so on. We know there are infinite number of energy levels in any atom. Okay. Usually, where this electron will be present, will it be present in lower energy or in higher energy? We know in hydrogen we have only one electron. Where this one electron will be there? In first shell or in any other higher energy levels? Usually electron will be present in first shell. Why so? Why it is like that? Why this electron is present in first shell and not in any other energy levels? See, what is the formula to calculate energy? En is equal to minus 13.6 Z square divided by N square, and unit of energy is electron volt. If the electron is present in first shell, minus 13.6, Z represents the atomic number. Here we are talking about hydrogen. So the atomic number of hydrogen is 1. So minus 13.6 into 1 square divided by, if the electron is present in first shell, the value of N is also 1. So 1 square. So electron which is present in first shell got minus 13.6 electron volt of energy. Okay. If the electron is present in second shell, then what will be the energy, Karnam? We are talking about hydrogen atom, so atomic number is still the same, but now the electron is present in second shell where N is equal to 2, so it is 2 square. So minus 13.6 divided by 4 is minus 13.6 divided by 4. What is the value? Minus 3.4 electron volt. Among these two values, which is the lower energy? Is it minus 13.6 or minus 3.4? Which is the lower energy?
Minus 13.6.
Very good. Minus 13.6 is the lower energy. If the electron is present in third state, then what will be the energy of the electron? 13.6 into 1 square divided by, since the electron is present in third shell, it is 3 square, which is 9. So what is the value? Minus 13.6 divided by 9 is minus 1.5 electron volt. So as we move away from the nucleus, the energy of the electron is getting increased. We know that energy and stability are inversely proportional, and electrons will be present at the lower energy level to make them stable. Okay, so electrons will be present in first state so that its energy will be least and stability will be maximum. Okay, so now electron is present in first shell. Okay, right, Kana. Now this is the actual energies of each energy level, but I'm going to write the hypothetical value. Listen here. For example, if the electron is present in first shell, let us say the energy is 10 unit of energy. If the electron is present in second shell, the energy is 30 unit. This is 50. This is 80. This is 100, and so on. For example, if this electron which is present in first shell have to move to second energy level, what this electron have to do? If the electron is present in first shell, its energy is 10. If the electron have to move to second energy level, energy has to be 30. So what this electron has to do? Energy of the electron has to get increased, right? So initially it is 10. Energy of the electron have to be increased to 30. So how to do that? This electron will absorb a particular amount of energy to get excited to the second energy level. So how much unit of energy this electron have to be absorbed to get enter into second energy level? How much energy this electron have to absorb, Karna? See, this electron got 10 unit of energy already. If this electron have to go to second energy level, energy has to be 30. So how many unit of energy this electron have to absorb?
20.
Very good. It is 20. So how you told that number 20? It is basically the energy gap between this shells, right? So energy gap is nothing but delta E final state minus initial state. Here final state is 30 because electron is moving from first state to second state. So second state is the final state. So which is 30 minus initial state is 10. So which is equal to plus 20. So whenever we are supplying or whenever the system is observing a particular amount of energy, it has to be positive. So here electron has to absorb 20 unit of energy to get excited to second energy level. Okay. Now this electron has to get excited to fourth energy level. How much unit of energy this electron has to absorb? It is present in second shell. if this electron wants to move to fourth energy level, what does electron have to do? How much unit of energy does this electron have to observe to get excited to fourth energy level? How much unit of energy have to this electron have to observe karna? 80 minus 30, right? It is plus 50, right?
Yes, ma'am.
So it is plus 50. Okay. Whenever this electron is moving to higher energy level, these electrons are uh, unstable, because whenever these electrons are getting excited, the energy of the electron is getting increased. Whenever the energy is getting increased, stability will be less, or stability is getting decreased, right? So whenever these electrons are getting excited, that electrons are unstable. So what these electrons will do, these electrons which are present in excited state will come back to the lower energy level or the ground state itself. If the electron is present in fourth state, lower energy levels are third shell, second shell. All these third and second shells were lower energy level, and first state is the ground state itself. For example, this electron have to move from fourth state to first state. How much unit of energy this electron have to release? Initially
70.
this got, yes, very good, it is 70. So delta E is equal to final status first shell, which is whose energy is 10, minus initial state energy is 80, so it is minus 70, which means minus 70 unit of energy, that is 70 unit of energy was released by the electron to move from fourth state to first state. So what we can understand from this transition is, whenever this electron is moving from lower energy to higher energy level, and energy is being observed, and if the electron is moving from or coming back to lower energy level, these electrons are losing its energy, right? So how much unit of energy have to get observed or released can be decided by the energy gap between them. Okay, that's it, Kana. So this is called as electronic transitions. Okay, so here if the electron is moving from lower energy level to excited state, energy is being observed, and if the electron is coming back to lower energy level, the electron is losing its energy. The energy what I'm talking about is nothing but electromagnetic radiation. Electron is observing a particular amount of a particular amount of energy, right? That energy is in the form of electromagnetic radiation. The energy observed and released by the electrons are in the form of electromagnetic radiation. Could you please tell me what are all the electromagnetic radiations you know?
Infrared rays, gamma rays.
Very good. Very good. What is your name, Kanna?
Seedana.
Sorry?
Seedana, ma'am.
Chitana. Okay. Now tell me.
Infrared rays,
Infrared,
X-ray,
X-rays,
gamma rays,
gamma rays, super,
UV rays.
UV, right? So these are all different types of electromagnetic radiations. But what is the difference between all these radiations, Kanna? We know X-rays are different from gamma rays. Gamma rays are different from, yes, Kanna?
Frequency,
Yes, frequencies are different. What else?
wavelength,
Frequency, wavelength, energy. All these parameters are called wave parameters. Okay, very good, Kana. So now we're going to discuss what is this electromagnetic radiation and what are all the wave parameters. Okay, basically electromagnetic radiation is nothing but, see, this is, let us consider this is electric field. Okay, so this is electric field, and this is magnetic field. Electric field and magnetic field are traveling perpendicular to each other. then this is called electromagnetic radiation. And as she told, we have so many types of electromagnetic radiations: radio waves, visible light, infrared, ultraviolet, x-rays, gamma rays. All these were electromagnetic radiations, but the properties of each radiations are completely different, right? So x-rays are different from visible light, x-rays are different from gamma rays. So basically, electromagnetic radiations are different in their wave parameters. Wave parameters are nothing but wavelength, frequency, wave number, and all that. Okay. So now we're going to see what are all the wave parameters and the relationship between them. Let us take one electromagnetic radiation. Okay. See, this is considered to be one complete wave. In one complete wave, this is called crest, and this region is called trough. Okay. So this is one complete wave, and this is another complete wave. This is another complete wave. Okay. So distance between two successive crest or distance between two successive trough is called wavelength. So wavelength is nothing but distance between two successive crest or two successive trough is called wavelength. Okay, and what will be the unit of wavelength?
Lambda. Armstrong.
Okay,
Lambda.
lambda is the representation of wavelength. Unit is
Armstrong.
not exactly. See, Armstrong can be the unit of wavelength, but what is that Armstrong?
Meter. Meter.
Very good. It is meter. So unit of wavelength will be meter. Angstrom is 10 power minus 10 meter, but wavelength can be expressed in any meter. It can be it can be any prefix. It can be nanometer, or it can be picometer. It can be angstrom. Anything is right. Okay. Basically, wavelength is expressed in meter. Okay. And frequency. How we can represent frequency? How we can represent frequency?
Yes.
No.
N, ma'am.
It is not n. Nu. This is frequency. See, listen here. All these waves are moving. Okay, they are not stationary waves, they are moving. Okay, now I'm going to consider a point here. In 1 second, how many complete waves are crossing this particular point is called frequency. Okay, number of complete waves crossing this particular point in 1 second is called frequency. See, this is a kind of wave. I'm going to draw another type of wave here. Could you please tell me which wave got highest wavelength and which wave got lowest wavelength?
A have highest wavelength. Graph B have lowest wavelength.
That's it. Which got highest frequency? Which got highest frequency?
The quite opposite, ma'am.
Yes. So second wave got highest frequency and this wave got lowest frequency. So what we can understand is wavelength and frequency are inversely proportional. So nu, that is frequency, is inversely proportional to lambda. I'm going to replace this proportionality symbol with a constant c. And c is nothing but velocity of light. Velocity of light. So what is the velocity of light? 3 into
3 10 power 8.
3 into 10 power 8 meter per second. Okay. So this is frequency and this is the relationship between frequency and lambda. Next is wave number. Wave number can be represented with a term nu bar. and it is the reciprocal of wavelength. Could you please tell me the unit of wave number then? Unit of wave number.
Per meter, ma'am.
Very good. Because unit of wavelength is meter. So 1 by meter is nothing but meter inverse. So in 1 meter, if you count number of complete waves, then that is the wave number. Okay. And what is the unit of frequency? What is the unit of frequency?
Ma'am.
Sorry?
Hertz.
Hertz, right. Apart from hertz, there's another unit. Second inverse.
Perfect.
Second inverse. Okay. And there is no conversion between hertz and second inverse. 1 hertz is nothing but 1 second inverse. Okay. That's it. And energy. Energy can be represented with the alphabet capital E, and energy and frequency are directly proportional. I'm going to replace this proportionality symbol with a constant h. E is equal to h nu. What is this h, Kanna? What is this h?
Planck's constant, ma'am.
Very good. It is Planck's constant. It is Planck's constant, and we know the value of Planck's constant, which is
6.626 into 10 power minus 34.
6.626 into 10 power minus 34 joule seconds. Okay, very good. And finally, time period. Time period can be represented with the symbol capital T, and it is the reciprocal of frequency. Now tell me, what is the unit of time period then? 1 by second inverse, which is seconds. That's it. So second is the unit of time period. And what will be the units of energy? What will be the units of energy? There are so many units now. We can express energy in terms of electron volt, energy in terms of joules, calories, ergs. We can use any of the units. Okay. So we have seen what is wavelength, frequency, wave number, energy, and time period. Now we'll see the relationship between them. So E is equal to h nu. See, Kana, this is the energy of one photon. To calculate the energy of n photons, E is equal to n h nu. N is nothing but number of photons. Okay. And we know E is equal to h nu. And I want to write this expression in terms of wavelength. How I can do that? Energy is equal to h into, in terms of wavelength. Nu can be written as C by lambda. Right? Energy is equal to h into C into 1 by lambda. 1 by lambda can be written as 1 by lambda can be written as, what is reciprocal of wavelength?
Frequency.
It is not frequency. Reciprocal of wavelength.
Wave number.
Very good. It is wave number. That's it. So from this expression, we can understand that energy and frequency are directly proportional. From this expression, I can understand that energy and wavelength are inversely proportional. And from this expression, I can understand that energy and wave number are directly proportional. And we can use any of these formulas to calculate wave parameters. Okay. It is we have to choose the formula based on the data given. Okay. Is that clear? Now I'm going to draw a wave pattern, and I want you to tell me the I want you to tell what I've written here, or what pattern you're observing. Kana, what is the pattern you're seeing here?
The wavelength is decreasing, ma'am.
Very good. In leftmost corner, wavelength is highest, and rightmost corner, wavelength is lowest. How about frequency?
Increasing.
On left side, frequency is low. On right side, frequency is high.
Which means how about energy? How about energy? Where energy is minimum, where energy is maximum? Where energy is minimum, where energy is maximum. See,
Right side energy is increasing.
Very good, Kana. We know that frequency and energy are directly proportional. Since frequency is lowest at the leftmost corner, energy will also be minimum. Here, energy will be maximum. How about wave number? How about wave number?
Wave number decrease, ma'am. In
Where
right
the
side. Right side wave number decrease, ma'am.
Kana, energy and wave number are directly proportional.
Right side wave number increase, ma'am.
Yes. So here leftmost corner wave number is lowest and here wave number is highest. That's it. Okay. So this is the electromagnetic spectrum. Electromagnetic spectrum. Listen here. We have seen so many types of electromagnetic radiations, right? So the electromagnetic radiation whose wavelength is maximum is radio wave. So radio wave got maximum wavelength and minimum energy. Okay. So in electromagnetic radiation, radio wave got maximum wavelength and minimum energy, minimum frequency. After radio wave, it is microwaves. After microwaves, it is IR. What is the full form of IR? What is the full form of IR?
Infrared rays, ma'am.
Infrared. After infrared, are visible light. After visible light, it is UV. After UV, it is X-rays. After X-ray, it is gamma ray. Right. So gamma ray got highest energy and lowest wavelength. Okay. And visible light is not the single component system. This got 7 components. Could you please tell me what are all those components?
WIBGR.
Yes. Could you please tell me the formula? Could you please tell me the spelling?
VIB
VIB
GYOR.
YOR. See, Kana, listen here. Red color has to be near to this infrared and violet color has to be near to this ultraviolet. Okay. See, from the spectrum, we can understand that radio wave got lowest energy and X-ray got highest energy. And among microwave and X-ray, which got highest energy? Among microwave and X-ray, which got highest energy?
X-ray.
X-ray. Among infrared and UV, which got highest wavelength? Infrared and UV, which got highest wavelength? Infrared, UV. Among these two radiations, which got highest wavelength?
Infrared.
Very good, Kana. Among visible light, which color got highest wavelength?
One more time, told ma'am.
Among visible light, we have 7 components, right? We have
Yes, ma'am.
7 colors. Among these 7 colors, which color got highest wavelength?
Red color.
That's it. That's it. So, are you guys clear? Any doubt, Kana?
No, ma'am.
Okay. So,
The slides
See?
before, ma'am.
this one?
Yes, ma'am.
Okay.
Thank you, ma'am.
See, here's the question. Yellow light emitted from the sodium lamp has the wavelength of 580 nanometer. See, wavelength is given as 580 nanometer. They're asking us to calculate frequency, wave number of this yellow light. Okay, so what is the relationship between wavelength and frequency? Nu is equal to C by lambda. And what is C? 3 into 10 power 8 meter per second divided by wavelength is 580. What is the value of nano? What is the value of nano?
10 power minus 9, ma'am.
Very good. It is 10 power minus 9 meter. So meter cancel. If you simplify this, you'll get the frequency in terms of centimeter inverse. That's it. And also we have to calculate wave number, right? So wave number is nothing but reciprocal of wavelength. So 1 by 580 into 10 power minus 9 meter. That's it. If you simplify this, you'll get the wave number also.
19.3 into 10 power 1, ma'am.
Okay, Kana, okay. If you're simplifying it, then you'll get the value. Super. Next, one more question. So here's the question. Find energy of each of the photons which corresponds to light of frequency 3 into 10 power 15 hertz. See here, frequency is nothing but 3 into 10 power 15 hertz. Instead of hertz, I can write it as second inverse. Right. Now from this frequency, we can calculate energy. What is the relationship between frequency and energy? What is the relationship between frequency and energy?
E is equal to HC.
E is equal to H.
C frequency.
C is not frequency. C is velocity of light. E is equal to H.
E equal to H mu.
So value of mu is given and we know the value of Planck's constant. If you multiply Planck's constant and frequency, you'll get the energy. Okay. In second question, wavelength is given. So here we have to use E is equal to H C by lambda. So we know the value of Planck's constant, we know the value of velocity of light, and wavelength is given as 0.5. Angstrom is, what is angstrom?
10 power minus 10.
Very good, 10 power minus 10 meter. And Planck's constant is 6.626 into 10 to the power of minus 34. What is the unit?
Joule
What is the
second.
unit? Very good, joule seconds. And velocity of light is 3 into 10 power 8 meter per second. So per second, second will get cancelled. Meter and meter will get cancelled. That's it. So if you simplify this, you'll get the value of energy in terms of joules. Okay. So this is how we have to use the wave parameters to calculate energy, wavelength, or the data. I mean, from the data, we can use the formula accordingly. Fine. So any doubt? Any doubt, Kana?
No, ma'am.
Fine. We'll do one more problem. Here the question is, what is the number of photons with the wavelength of 4000 picometer that provide 1 joule of energy? Could you please calculate and tell me the number of photons? Number of photons. We saw only one formula related to this number of photon.
$26,504, ma'am.
26,500. No, Kana. What is the formula?
And E
What
is
is
equal to NH.
NH? Formula Z is equal to NH nu, right?
Yes,
And
ma'am.
instead of nu, I can write it as C by lambda, right, Kana?
Yes, ma'am.
So we have to calculate N. So
N.
E into lambda divided by H into C, which is equal to number of photons. So number of photon is equal to what is the value of energy? It is 1 joule.
1
And
joule.
what is the value of lambda? It is
4,000.
4,000. 4 into 10 power 3. Pico is 10 power minus 12 meter divided by Planck's constant is 6.626 into 10 to the power of minus 34 joule seconds, and velocity of light is 3 into 10 power 8 meter per second. So meter will get cancelled, second and second inverse will get cancelled, joule and joule will get cancelled. That's it. So simplify this and let me know the value. See, this is 4 into 10 power 3 into 10 power minus 12. This can be written as 6.6 into 3. I'm just bringing this 10 powers to the numerator. It is 10 power plus 34 and it is 10 power minus 8. So simplify this and tell me the values, Kana.
$49.6 into 10 power 51.
No, Kana.
Nearly 2 into 10 power 17, ma'am.
If you are telling me it is 2 into, then please check 10 power value now. Power of 10 is not. You told me it is 17, right?
Yes, ma'am.
2 into, it is not 17, Kana. It is 2
51,
point
ma'am.
something. No, Kana, no. See, here, this is 10 power. This is 10 power 3, this is 10 power 34. So it is 37, right? So into 10 power, it is minus 12, it is minus 8. So it is minus 20. Simplify this. 37 minus 20 is?
17 is 17.
It is just 17, right? It will not be 50 something.
Okay.
Who told me it is 2 point something?
It's me, ma'am.
Send them, children. Kana, see, if you simplify this 10 powers, you will get 10 power 17, right? Here, the numerator value is less than denominator. So definitely you'll be getting the answer in terms of 0 point something. If the answer is 0 point something, then the value is 10 power 17. But you told me it is 2 point something, right? So which means you're moving the decimal towards right, which means it will be 10 power 16. The number after simplifying, you'll get 0.2 something, Kana. So answer is 0.2 into 10 power 17. If you want to express in terms of 2 point something, then 2 point something into 10 power 16 photons. This is the answer. Any doubt? Send them, children.
No, ma'am.
Right. Can any other doubt?
Ma'am.
Shall we move on to next question? Bhumika, any doubt, Kana? Mumtaz? Rakshin? Any doubt, Rakshan?
No doubt, ma'am.
Okay. So shall we move on to next concept? Now we're going to discuss the topic called hydrogen spectrum. In hydrogen atom, how many energy levels are there? Infinite number of energy levels are there, right? How many electrons are present in hydrogen?
One.
Only one. Okay, this is my first shell. This is second shell. This is third shell. This is fourth shell. This is fifth shell. This is sixth shell. This is seventh. And so on. It will be there till infinity. Okay. We have only one electron in this hydrogen atom. If this electron is observing any kind of electromagnetic radiation, definitely this electron will get excited to any of the energy levels. For example, if the electron is getting excited to sixth state, will it be stable? Will this electron be stable in n is equal to 6? Will it be stable in sixth shell, Kana?
No,
No,
ma'am.
ma'am.
Definitely not. Because if the energy is getting increased, then stability is getting decreased. So to get the stability back, this electron may come back to the any of the lower energy levels or to the ground state. So what are all the possibilities? This electron may come back to fifth energy level or fourth, or it can come to third, or it can come to second energy level, or it can come back to first energy level, right? See, there are so many transitions possible. See, first of all, the excitation itself, we have so many other possibilities. Electron may go to second energy level, or it can excite it to third, or it can excite it to fourth, or it can go to infinity also. And also coming back to lower energy also, we have so many transitions possible. So what we're going to do here is we're going to divide this transitions into different set of transitions. Listen here. The N1 is going to be the lower energy level, and N2 is going to be higher energy level. I'm going to segregate all these possible transitions. Okay. I'm going to segregate all these transitions in particular series. Listen here. The N2, what I'm going to mention is higher energy level, and the N1 is going to be the lower energy level. Electron, after observing a particular amount of energy, electron can go to any of the excited states. Okay. From any of the excited states, it can come back to N is equal to 1. Okay. If the electron have to come to the first energy level, minimum electron has to be in which energy level? At least electron has to be in second energy level, right? So electron can come from second energy level to first energy level, or it can come from third energy level to first energy level, or it can come back from fourth to first energy level, or electron can come from infinity to first energy level also. See here, the lower energy level is constant, but higher energy level can be 2, 3, 4, 5, 6, etc. And this kind of transition or this kind of series is called Lyman series. And in this transition, what this electron will be doing, it will absorb energy or it will release energy. In these
Releasing.
transitions, yes, electrons will be releasing energy because electron is coming from higher energy to lower energy, right? So it will release the energy in the form of ultraviolet radiation. So if they are talking about the transition where electron is losing ultraviolet radiation, then they are talking about Lyman series where the lower energy level is 1. So this is a particular set. Now I'm going to talk about another set where the electron is coming to the second energy level. Okay, so if the electron has to come back to second energy level, what will be the minimum excited state? From which energy level it can come back to second energy level? Minimum electron has to be, very good, electron has to be third shell. So third to second, or fourth to second, or fifth to second, or infinity to second, all these transitions are coming under the series called Balmer series. And in this transition, electron is releasing visible radiation. Super. Here the value of N1 is 2. Electron is coming from excited state to second energy level. Next series is the electron is coming from excited state to third energy level. So the first transition will be fourth to third energy level, fifth to third energy level, sixth to third energy level, or infinity to third energy level. And what kind of series is this? What kind of series is this? Bastian series. And here the electron will be losing, or it will be releasing infrared radiation. More specifically, it is called as very near IR. Okay. Fourth series is electron is coming from excited state to fourth energy level. So the minimum transition will be fifth to fourth, sixth to fourth, seventh to fourth, or infinity to fourth. So this kind of series is called bracket series. And here it will emit infrared. Fifth series is electron is coming from excited state to fifth state. So minimum transition will be sixth state to fifth state, seventh state to fifth state, or eighth shell to fifth shell, or infinity to fifth shell. And this kind of series is called fund series. And here also electron will be releasing, or yes, it will be releasing infrared, and this is called far infrared, far IR. And last series is excited state to electron can be moved to sixth shell. So what will be the minimum transition?
6.
Seventh to sixth, eighth to sixth, ninth to sixth, or infinity to sixth shell. And this kind of series is called Humphrey series. And here electron will be releasing very far IR. That's it, Kana. So they'll give you any transition and they may ask you what kind of energy that electron is releasing, or they may ask you to calculate the wavelength of that particular radiation or wave number of that particular radiation. Okay, anything we can expect. For example, if the electron is coming from fourth state to second state, could you please tell me what kind of series is this? Electron is coming from? Yes.
Balmer.
Very good, Kana. Balmer series. And in this transition, electron will be releasing visible light, right? So they may ask you how much energy this electron is losing. So how you will be calculating the energy?
4 minus.
Yes. So we know have to calculate change in energy, right? So we can calculate final energy minus initial energy. So we know how to calculate the energy of second state. We know how to calculate the energy of fifth state. And by just subtracting, we know how much energy was released during this transition. And from this energy, we know the relationship between energy, frequency, wavelength, and all that. So from this energy difference, we can calculate how much frequency was released or how much wavelength was released also. You're getting my point? Not only energy difference, Kana, we can calculate frequency, wavelength for this particular transition. Because we know the relationship, right? Since it is delta E is equal to h nu. So using delta E, we can calculate frequency. Or using delta E, we can calculate wavelength. I mean, C by lambda. Using this energy gap or energy difference, we can calculate wavelength. Using this energy gap, we can also calculate wave number. Anything is possible. Okay, but for that calculation will be a little lengthier one. So to make the calculation simple, we came up with one formula, which is a very famous formula. That is the only formula which is related to this hydrogen spectrum, which is 1 by lambda. This is the formula to calculate. What is this? What is this 1 by lambda represents?
Wave number.
Very good, wave number. So this is the formula to calculate wave number. So wave number is equal to Rydberg constant into Z square into 1 by N1 square minus 1 by N2 square. That's it. So this formula was, it is basically came from this formulas only. So they have derived this formula based on Bohr's concept or Bohr's formula. And what is the value of Rydberg constant?
1.1 into 10 power 7 meter.
Very good. 1.097 into 10 power 7 meter inverse. And N1 is nothing but lower energy. N2 is nothing but higher energy. And what is this Z represents?
Atomic mass.
Very good. Atomic number. Atomic number. Z represents atomic number. See, writing the atomic number in the formula is very important. Though the atomic number of hydrogen is 1, we should not neglect this the term Z here, because they may give you the data regarding helium 2 plus, helium plus also. Helium plus is also a single electron system where you can use this formula. Okay, but atomic number is not 1, it is 2. So we have to substitute the value of atomic number here. So whenever you are memorizing the formula, please memorize along with the atomic number. Okay, fine. So if this transition is given, this is the value of N2 and this is the value of N1, and they are talking about hydrogen, then atomic number is 1, and we know the value of Rydberg constant. In some of the cases, they may give you the Rydberg constant value also. If they are giving any value to the Rydberg constant, please use that exact value in your calculation. Okay, that's it. Here, the tricky part is finding the values of N1 and N2. They will not give you the transitions directly. They'll give you the clues to find the value of N1 and N2. That is the most critical part there. In finding the values of N1 and N2, most important is N2, because N1 is very easy. They may give you the name of the series. If they tell you it is about Lyman series, then what will be the value of N1?
1.
That's it. Or they'll give you what kind of radiation was emitted. For example, the electron is releasing visible light, then what will be the value of N1?
2, ma'am.
2. So finding the value of N1 is very easy, but value of N2 is little tricky. Listen here, the clues will be like this. This is Lyman series, right, Kana? In Lyman series, electron is coming from second state to first state, right? See, this is called as first line of Lyman series, or alpha line of Lyman series, or H alpha line of Lyman series. This transition is called as second line of Lyman series, or beta line, or hydrogen H beta line. Okay, this is third line of Lyman series, or it is also called as gamma line or H gamma line. Okay, so clues will be like this: first line of Lyman series, or alpha line, or H alpha line. So from this clue, we have to understand the value of N2. Okay, now also, I'm going to draw few transitions and I want you to tell what kind of series is that.
Balmer.
Very good, it is Balmer series. So electrons are coming from excited state to second shell. So this is Balmer series. So in this Balmer series, could you please tell me which is the first line of Balmer series?
3.
A transition. You have to tell me the transition completely.
3 to 2.
Very good. Third shell to second shell is the first line of Balmer series. Okay, fine. Very good, Kana. Okay. In these transitions, which transition got lowest energy? Which transition got lowest energy?
3 to 2.
Very good, Kanna. So they may give you clues like in Balmer series, the lowest energy transition. So lowest energy transition is nothing but 3 to 1. I mean 3 to 2.
3 to 2.
And also this is the highest wavelength transition, right? Energy is lowest, then energy wavelength will be highest, right?
Yes, ma'am.
How about wavelength? I mean, how about wave number?
Increase.
If here in
Increase.
no. See, energy is very
Decreases, ma'am.
yes. So in this transition, that is third shell to second shell, if electrons are coming to second state from third state, then this transition got lowest wave number because energy is lowest, right? We know E is equal to H C nu bar, right, Kanam? Okay.
Okay.
And in this transition, which got highest energy transition, which is the highest energy transition?
Infinity to 2, ma'am.
Infinity
Very
to
good.
2.
Infinity to 2. This is the highest energy transition. Or highest wave number transition. Or lowest wavelength transition. Okay. Or this is also called as series limit of Balmer series. So this is the last transition. So this is called series limit of Balmer series. Okay, so this is the last transitional Balmer series. They'll give you any of these clues to find the value of N2 and N1. Okay, is that clear? Any
Yes, ma'am.
doubt?
No, ma'am.
Okay. So we'll do one problem. Calculate the wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. Okay. Could you please tell me what transition they are talking about?
Balmer 3 to 2.
Okay, they're talking about Balmer series. So the transition is N2 to N1, and here the value of N1 is 2. And which got highest wavelength transition? The transition whose energy is lowest, which is
Lowest.
3 to
3
1.
to 2.
That's it, 3 to 2 transition. And they're asking us to calculate just the wave number, and we have the direct formula. So wave number is equal to Rydberg constant into Z square
Z square,
into
1 by
1 by N1 square minus 1 by N2 square. That's it. That's it, Kana. So please calculate and tell me the value of wave number. Tell me approximate value, that is enough.
$7.1.
Mhm. It is not 7.1.
0.13 mm.
0.13. Is there any 10 power terms?
10 power minus 7. 7 mm.
Yes, it is right. It is right. You told me it is 0.13
1
into 10 power.
7.
Yes, right, Kana. So original answer is 0.15 into 10 power 7 to 0.13. Approximately it is right. Okay. Any doubt? Rakshan, Bhumika. Any doubt, Kana?
No, ma'am.
Okay, fine. Shall we move on to next concept? See, today we will complete all the concepts, and in next class we'll be discussing only numerical from atomic structure. Okay, we're going to see a lot of MCQs from atomic structure. So today we'll complete all those pending concepts. Okay. Next concept we're going to discuss is Heisenberg's uncertainty principle. Kana, what is this? What principle is this?
Ma'am, it is impossible to determine the momentum and position of microscopic particle simultaneously, ma'am.
Very good. If you try to do so, what will happen?
Certain error will come, ma'am.
Very good. That's it. See, if a microscopic particle is moving, then we cannot measure a couple of physical properties simultaneously. The properties they are talking about is position and momentum. If you try to measure these two properties simultaneously, then there will be definitely a significant quantity of error. Okay, there will be a lot of error in that. Okay, so that is Heisenberg's uncertainty principle. And what is the mathematical expression for that? Position is represented with the term x and momentum is p. Okay, and what is the mathematical expression? Uncertainty in position into uncertainty in momentum is greater than or equal to
H by 4.
very good. That's it. And also, we cannot measure energy and time simultaneously. So, based on these two parameters, we can write Heisenberg's uncertainty principle as uncertainty in energy, uncertainty in time, which is greater than or equal to h by 4 pi. This is also right. Okay. And this is momentum. And what is the expansion of this momentum?
MV.
Very good, Kana. Here, this particle is moving linearly. So the momentum which is associated with this particle is linear momentum, which is mv. But here, there's an uncertainty, change in momentum, right? See, change in momentum is equal to, if the particle is moving, mass of the particle will not change. There will not be any error in the mass. But velocity will get changed. So delta P is equal to mass into delta V. So this is the expression. So this can also be written as delta X into mass into delta V, which is greater than or equal to h by 4 pi. See, here they are talking about only microscopic particle. For microscopic particle, we cannot measure the position and momentum simultaneously. If you try to measure that simultaneously, then there will be error in the values. Okay, but if it is for macroscopic particle, we can measure simultaneously and there will not be any significant errors. Okay, you're getting my point? If the microscopic particles, say electron, atom, molecule, for these systems, we cannot measure position and momentum simultaneously. If you try to do so, then there will be a significant quantity of error. But if it is a macroscopic object, for that, we can measure these position, momentum, energy, and time simultaneously. There won't be any issue. Okay. error will be very minimum for macroscopic objects, but it is not in the case of microscopic object. Okay, this is the Heisenberg's uncertainty principle. Any doubt? Okay, so they may give you position and they may ask you to calculate uncertainty in momentum, or they may give you the uncertainty in velocity and they may ask you to calculate delta x. Okay, fine. Okay, shall we move on to next concept? Now, what is de Broglie's wavelength? What is de Broglie's wavelength?
Lambda is equal to h by m.
Very good, Kana. Have you got that value? I mean, have you got that formula or relationship?
E is equal to mc square.
Very good, very good. See, wave got dual nature. Electron got dual nature. Electron will be behaving, can behave like wave, and also it can behave like particle, right, Kana? So if it is behaving like a particle, then this formula is applicable, or this relationship is applicable. E is equal to mc square. If it is behaving like a wave, then E is equal to h nu. So here left sides are same, so right side is also same. So h nu is equal to mc square. Nu can be written as c by lambda. So here 1c and this 1c will get cancelled. So h by mc, which is equal to lambda. That's it. So this is de Broglie's wavelength, lambda. H is Planck's constant. M is mass of the particle, and c is velocity of that particle. Okay. See, if the velocity of the particle is 3 into 10 power 8 meter per second, we can use the term c. Or if the particle is moving in any other velocity, then formula is h by mv. Or this can also be written as h by mv can be written as momentum. That's it. That's it. Okay. We'll do one problem now. A microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? From which concept this question is asked?
Heisenberg.
Very good. So what is the only formula we know which includes velocity and the position?
Del x. Del v.
M del v.
M del v.
Which is equal to h by 4 pi.
4 pi.
That's it. So here we have to calculate uncertainty in velocity. Right. And here they are talking about electron, which is a microscopic particle. Right. So here delta x is nothing but 0.1 into 10 power minus 10 meter. And here what is m? What is m? Basically, what is m?
Mass.
Mass. Here?
Minus 1.6.
Here mass of an electron. Mass of an electron is 9.1 into 10 power minus 31 kilogram. Okay. Here we have to calculate delta V. So delta V is equal to h by 4 pi into 1 by m into 1 by delta x. Right, Kana? So we know the value of Planck's constant, which is 6.626 into 10 to the power of minus 34. What is the unit?
Joule second.
Okay, but we should not use that unit here because in denominator we have mass. And what will be the value of mass? It is 9.1 into 10 power minus 31 kilogram. Since in denominator we have a kilogram unit, Planck's constant also has to be in terms of kilogram. So we can do that. How joules can be written as kilogram meter squared second power minus 2. Unit of Planck's constant is joule seconds, right? So unit of joule, I can write it as kilogram meter squared second power minus 2 into seconds. 1 second and 1 second inverse will get cancelled out. So what will be the unit? Kilogram meter square second power minus 1. That's it. So 4 into what is the value of pi?
3.14.
Yes, it is 3.14. Mass of an electron is 9.1 into 10 power minus 31 kilogram. And position is 0.1 into 10 power minus 10 meter. That's it. So here kilogram will get cancelled. Meter and 1 meter will get cancelled. Right. That's it. You'll get the unit in terms of meter per second, that is the unit of velocity, right Kana? After simplifying, you'll get the value of uncertainty in velocity. Okay, so in numerator we have 6.6. In denominator we have 4 into 3. I'm just rounding off this 3.14 to 3 and 9.1 to 9. Okay, and in numerator we have 10 power minus 34. I'm just bringing this 10 power minus 31 to the numerator, so it is 10 power plus 31. And here it is, see, this is 10 power minus 1, right Kana? This is 10 power minus 1, so it is 10 power minus 11. I'm just bringing that to numerator, it is 10 power plus 1. So could you please tell me the approximate value? Approximate value is enough.
Zero 0.067.
10 power?
2.
Not exactly.
6 into 10 power 5, ma'am.
That is not 10 power 5, Kana. Can you please check again?
Six into 10 power 4, ma'am.
No. 6 is right, but there is some mistake in 10 power.
Ten power 1, ma'am.
No. See, if you simplify this 10 powers, what you'll get?
2.
See, it is 10 power minus 34 and 31 plus 11.
11, ma'am. I think 1.
Rakshan, what answer you're getting, Kana?
8, ma'am.
Yes, if you simplify this 10 powers, you'll get 10 power 8 meter per second. And what answer you're getting after simplifying these numbers?
0.06.
Yes, it is 0.06. Right. If you want to express in terms of 6 point something, then 6 into 10 power, you're moving this decimal
Minus 2.
towards right. So you have to decrease 2 numbers from this 8. So it is 6.
6.
That's it. Kana, listen here. Listen here. Here they are talking about this microscopic object, and for this microscopic object, if the uncertainty in position is 0.1 angstrom, then uncertainty in velocity is very huge, which is 6 into 10 power 6 meter per second. Right? See, the uncertainty, that is the error, is very huge. Right, Kana? Now I'm going to give you another problem where we have to calculate uncertainty in velocity. Here the problem is a golf ball has a mass of 40 gram. It is not a microscopic object, right? So they are talking about a ball whose mass is 40 gram and the speed of it is 45 meter per second. If the speed can be measured within accuracy of 2%, they're asking us to calculate the uncertainty in position. So what is the formula? Delta x into m del v, which is equal to
h by 4.
that's it, Kanna, h by 4 pi. So we have the value of delta. Okay, we have to calculate delta x, right? And we know the value of m, which is 40 gram. And we have to know the value of delta v. See, they've given the velocity and they've given the accuracy. To calculate uncertainty in velocity, multiply this 45 with the accuracy. Accuracy is 2%, that is 2 divided by 100. So this will be the value of delta V. Okay. And please convert this gram into kilogram because Planck's constant, you'll be expressing it in a kilogram, right? So we have to convert 40 gram to kilogram. And here we have to calculate delta x. Delta x is equal to h by 4 pi into 1 by mass into delta V. So h is 6.626 into 10 to the power of minus 34 kilogram meter squared second power minus 1 divided by 4 into 3.14 into mass is, see, mass you have to express it in kilogram. So 40 kilogram, and what is the value of kilo? It is 1000. You have to write the value 1000 in denominator. So it's just 40 kilogram. I'm just bringing the value to the numerator because 10 power 3 is in denominator. So I'm just bringing that to numerator. It is 10 power 3. And what is delta V? It is 45 into 2 divided by 1000. That also I'm bringing to numerator. That's it. So what are all the common units? Kilogram will get cancelled. What else, Kanna? Meter per second. Delta V will be in meter per second, right? Here 1 second inverse and 1 second inverse will get cancelled, and 1 meter and 1 meter will get cancelled. That's it. Answer will be in meter. So 6.6 in denominator we have 4 into 3.14. I've just rounded off to 3. 40, 4 into 10, 45 into 2. And numerator we have 10 power minus 34, 10 power 3 plus 10 power 2. It is 10 power 5.
Kavita, you switch off your mic, Kavita. It's creating noise. Carry on, madam.
Okay, sir. So if you simplify this, what value will be getting? Tell me the approximate value. That is enough.
1.38 into 10 power minus 32, ma'am.
1.38 into 10 power minus
32, ma'am.
32. Check the power of 10. Yes, Rakshan, come again.
10 to the power minus 29.
No.
Minus 26. Minus 26.
See, 34. No, sir. Actually, 34 minus 5 is obviously 29. But after simplifying all these stuffs, we have to come up with the final answer.
Yeah, minus 20. Another 3 digit of four zeros should be.
Yes, sir.
Maybe
Yes.
26 or 25 like that.
Senthil Chelvan was partially right, but there is a minor mistake in the power of 10.
28 mm.
No, Kanna.
Yeah, it is 26. Minus 26, I think.
After dividing all this stuff, sir.
5,000.
26 itself, ma'am.
Okay, is it minus 26 or plus 26?
Minus 26.
Minus 26, ma'am.
See, here in this first problem, they are talking about the microscopic object, which is electron. And here the uncertainty was huge, right? But here they are talking about golf ball and it is not a microscopic object, right, Kana? Here it is a macroscopic object, and for this macroscopic object, we can measure position and velocity simultaneously, and the error will be minimum. And you told the values in terms of minus 27, right? So Heisenberg's uncertainty principle is applicable only to microscopic particle and not the macroscopic particle. So for macroscopic particle, we can measure position and velocity simultaneously, and error will be very, very negligible. We can measure it simultaneously, no issues. But as far as microscopic particles are concerned, whenever you're talking about electron or whenever you're talking about atom or molecule, we cannot measure position and velocity simultaneously. Okay, that's it. So we are done with this Heisenberg's uncertainty principle. Okay, we have only one concept, which is photoelectric effect. We'll discuss that in next class. And that is the only topic pending, right? And as I've told you already, in next class we'll be discussing lot of MCQs from this atomic structure. So please make sure you have revised all these formulas and all that. Okay, and please revise all those concepts also, Kana. So we'll meet next class. Okay, if you have any doubt, please ask me. We'll clear here. Rakshan, Bhumika.
It's 10 to the power minus 26, ma'am.
Come again, Rakshan.
It's 10 to the power minus 26, ma'am.
Okay, right. It is 10 power minus 26. Okay. So obviously value is very minimum, right? It is very less.
Thank you, madam.
Okay.